Hello, everyone. My name is Akram Ismail, and welcome to my MIT Summer Research Program talk. My summer work involved estimating electron transfer kinetics for flow battery electrodes using dense carbon films. To start us off, fossil fuels have historically been the main source of electrical power for residential and commercial use. However, renewables are beginning to play a larger role in the delivery of electrical power to the grid. The intermittency of renewables is the main challenge, which can scale for seconds, days, up to seasonal length, and it is essential to buffer the delivery to the grid by using energy storage technologies. Enclosed lithium-ion batteries are capable of storage in seconds, hours duration. Pumped hydroelectric storage is also widely used. The focus of this talk, however, will be redox flow battery technologies, and the main takeaway here is that the price and lifetime of the storage technology will be paramount in its final integration into the main grid. RFBs have electroactive species dissolved in supporting electrolytes and stored in independent tanks, which are pumped into the reactor between the tanks for storing and releasing energy by respectively charging and discharging the tanks. Some significant advantages of RFBs include their decoupled energy capacity and power. They have a long cycle life and durability. They are location independent, unlike hydroelectric power, as well as simple manufacturing, unlike lithium-ion batteries, which require precision manufacturing. Within the RFB, the porous carbonaceous electrode is a vital component where some of its roles include providing surface area for redox reactions, distributing electrolyte, and conducting heat and electrons. Important performance determining metrics include surface area, activity and selectivity, electrical conductivity, as well as permeability. Understanding reaction kinetics of the electrode is crucial towards improving RFB output and lowering costs. However, reaction kinetics are driven by interplay of factors, and the complex geometries of porous electrodes invalidate assumptions in conventional voltammetric techniques. With these challenges and limitations in mind, the objective of this project was to develop an approach for estimating electron transfer kinetics using electrode materials reminiscent of those used in RFBs. The methodology involves two main parts. First, a bottom-up synthetic process was developed to produce non-porous and planar carbon films. The first step involved mixing polyacrylonitrile and dimethyl formamide into a viscous solution. Next, the viscous solution is casted onto a clean glass surface under an inert environment until it dries into a polymer film. The third step involves thermally stabilizing the polymer disc in a muffle furnace at a temperature of 270 degrees C. The average retention here was 81% with a standard deviation of 7%. Finally, the thermally stabilized discs are carbonized under nitrogen at a temperature of 1050 degrees C to form the non-porous and planar carbon films, where the average retention was 66% with a standard deviation of 5%. An in-lab customized cell architecture was used with the synthesized electrodes, whose schematic is as shown below. The main components include titanium conductor plates on both ends, three sets of rubber gaskets, plastic compartments which function as the electrolyte domain, a port where the reference electrode is connected, a platinized titanium mesh that functions as the counter electrode, and aluminum plates on both ends as a mechanical reinforcement for the overall cell architecture. And finally, the synthesized dense band electrode disc that functions as the working electrode to complete the three electrode voltammetric analysis. First, in the dense film material characterization, a suite of spectroscopy was carried out to characterize the dense carbonaceous electrodes. The SEM cross-section on the left clearly shows that the synthesized electrodes are in fact dense. Further magnification of the SEM on a nanometer scale shows that the carbon structure is amorphous and semi-crystalline. Next, the wide-angle XRD spectra shows two peaks at the carbon crystallographic planes 002 and 10L respectively. Thirdly, the Raman spectra further shows two characteristic carbon bands, that is the D band and the G band at around 1600 per centimeter. In addition, the XPS spectra on the right indicates the presence of carbon, nitrogen, and oxygen function groups as expected for the bottom-up synthetic procedure described for producing the carbonaceous, non-porous, and planar carbon films. The electrochemically active surface area was also estimated. A blank 1 molar KCl electrolyte solution was analyzed using cyclic voltammetry to experimentally measure the specific double layer capacitance. The negative and positive non-Faraday currents were extracted at 0 volts, and the average capacitive current IEDLC was calculated. The electrochemical double layer capacitance was calculated using a linear fit, and the specific double layer capacitance was estimated experimentally to be 29.7 plus or minus 4.6 microfarads per centimeter square. The synthesized non-porous and planar carbon electrodes were tested in iron-based electrolytes. In the quasi-reversible regime, 15 millimolar iron chloride in 1 molar KCl was analyzed. First, a CV analysis was carried out to determine the anodic and cathodic peak-to-peak separation. The peak anodic and cathodic currents were also extracted by background subtraction of the non-Faraday current contribution using a linear baseline. Next, the Randall-Sevcik analysis was done where the peak currents were plotted against the square root of the scan rates. Here, scan rates in the range of 5 to 1 millivolt per second were plotted in order to determine the oxidative and reductive diffusion coefficients. From the equation below, the diffusion coefficients can be calculated from the slope of the linear fit. Lastly, Nicholson's method was used where Nicholson's dimensionless parameter psi was calculated using the peak-to-peak separation obtained from the CV, and the plot against the inverse of the scan rate square root was generated. The kinetic rate constant was then calculated using the slope from the linear fit in the Nicholson's plot, combined with the diffusion coefficients obtained from the Randall-Sevcik analysis. In the reversible regime, 10 millimolar ferro ferricyanide in 1 molar KCl was analyzed. Firstly, the CV plot indicates reversible behavior as shown where the peak-to-peak separation was around 57 millivolts as expected. In addition, the electrochemical impedance spectroscopy was also carried out, which was used to determine the charge transfer resistance of the system. Here, a Randall circuit was used to obtain an equivalent circuit fit to the experimental data from which the charge transfer resistance was extracted. Finally, the kinetic rate constant for the reversible regime was calculated using the equation as shown. Using the traditional methods of cyclic voltammetry and electrochemical impedance spectroscopy, the estimated kinetic rate constants obtained for the ion-based electrolytes are shown in the first two rows. As referenced in the table, these values are in agreement with previous work reported in literature, which validates the kinetic model developed to estimate the electron transfer kinetics for flow battery electrodes using dense carbon films. In conclusion, bottom-up synthesis method allows for consistent and high throughput production of the porous and planar carbon films. We also can say that the synthesized films are semi-crystalline, carbonaceous materials containing nitrogen and oxygen functional groups as seen with the suite of spectroscopy. A cell architecture enables evaluation of the dense films in the three electrode setup as the traditional voltammetric techniques were applied. Electrochemically active surface area of the dense films can be estimated using double layer capacitance. And finally, the electron transfer kinetics have been assessed in ion-based electrolytes as shown, relevant for RFBs in both the quasi and reversible regimes. Future work involves testing various electrocatalysts deposited onto electrodes for use in diverse chemistries, something which we are particularly interested in, experimenting with methods to increase the mechanical robustness of films and quantify performance changes is also another avenue to explore. And finally, I'd like to acknowledge the NSF funding, particular mentions to the Brushed Research Group for their supervision throughout, particularly my PI, Dr. Fikile Brushed, my primary supervisor, Charles Wan, as well as Alexander Quinn for being my supervisor. And special thanks to the MIT Summer Research Program for this invaluable opportunity. And yes, finally, if you have any questions, feel free to send me an email and I will love to chat about my work that I did at MIT. Thank you very much for listening to me. Bye-bye.